This is the Smart Buildings Academy podcast with Phil Zito, episode 460. Hey, folks, Phil Zito here. Welcome to episode 460 of the Smart Buildings Academy podcast. In this episode, we are going to be continuing our technician onboarding series, and we're going to be talking about building automation system input types. Last Wednesday, we talked about building automation systems in general. And over the next couple sessions, we're going to be going through input types, output types, and the different tiers of the architecture. Then we're going to move into electrical. Then we're going to move into HVAC. And then we're going to talk about some basic building automation functionality. As always, everything is going to be available at podcast.smartbuildingsacademy.com/460. I do realize I am 2 episodes behind on uploading those to iTunes or Apple Podcasts, Spotify, and our website. Just been insanely busy. Just had a lot of stuff going on with the kids and work, but I will get those uploaded. As always, they'll be available on YouTube and Facebook and on LinkedIn. So, couple housekeeping things. First off, we have our first YouTube channel member, Thomas Trang. Thank you very much. For those of you who want to support the Smart Buildings Academy podcast on YouTube, there are multiple different member tiers that you can sign up for. The highest tier actually has access to a Discord that I'm in, that you can interact with me throughout the day. You can interact with one another throughout the day. But it's just a way to help support the podcast and the resources that we dedicate to bring this to you twice a week for free. As always, if you find this valuable, please consider hitting the subscribe button and the notification bell on YouTube, sharing this on Facebook and LinkedIn by hitting the share and tagging at Smart Buildings Academy, or going to Apple Podcasts or Spotify and leaving us a 5-star review. Like I said, today we're going to be going through a lot of stuff. We're going to start off with a PowerPoint. I'm going to double check that audio is coming in good and on both LinkedIn and Facebook. Sounds good on YouTube and sounds good on LinkedIn. So let's get started. Building automation system input types. By the time you finish today's session, you're going to understand the common types of inputs and identify the requirements of different input types. We're going to look at logical and physical inputs. We're going to look at a specification, how to read it, and then how to identify inputs, what type of sensors and devices you need to purchase. And we're going to talk about the logical inputs and what those are and what they entail. There's 2 primary types of inputs. I do recognize that these are called different things by different organizations. So I will do my best to be agnostic in the naming. Do realize that depending on the vendor, they may be called different things. So please do give me some grace if I do not use the exact term that you would use. It's just because there's so many different terms to calling things in this industry, unfortunately. So I try to be as generic as possible. There's 2 primary types of inputs, and those 2 primary types of inputs are going to be the physical. Oops, here we go. Let me hit that real quick. The physical and the logical inputs. And the physical inputs are inputs that physically exist to connect a device to the building automation system. These are going to be things like your temperature sensors, like your pressure sensors, your current switches, your current sensing relays. Logical inputs are inputs that exist only in software to provide data and or settings for the building automation system. So this may actually represent a physical input that you gather from maybe a chiller or an air handler via BACnet or Modbus or LAN integration or MQTT integration. That's popular nowadays. But at the end of the day, where you're looking at them, they are logical. You are not physically connecting to that chilled water supply temp. The chiller is actually connecting to it, and it is interpreting it in its microcontrollers and sending it across some sort of communication bus to you. And so the input you're seeing is logical. So those exist, like I said, to provide data and or settings for the building automation system. All right. There's got to be a way to turn off this pointer so I don't have to keep going back to Slide Master. Let's see. We're just going to do the mouse cursor because it's easier for me rather than getting the pointer every time. And the grabbing the pointer just distracts me. We see right here the input portion of a Distech controller. We see resistive, voltage, current, contact, and pulse are the most common physical inputs. There are other physical inputs, but these are the most common ones we're going to run into. I'm going to give you a representation of these. So there's resistive inputs, of which there's really three types. There's thermistors, RTDs, and thermocouples. We're going to focus in on thermistors and resistive temperature diodes, or RTDs. Of the thermistors, there's a NTC and PTC. You could argue that for RTDs, some of those have NTC and PTC. That's negative temperature coefficient and positive temperature coefficient. We can see a negative temperature coefficient right here. Or actually, is this a positive one? Am I reading this backwards? I do not like this chart. No, no, no. I'm reading this right, right? As resistance goes down, temperature goes up. Yeah, negative. I'm not good with math, folks. Forgive me. Negative temperature coefficient, if I could speak, you'd think I could after this many podcasts. As the resistance goes up, the temperature goes down. And as the resistance goes down, the temperature goes up. You will most commonly see negative temperature coefficient used with temperature sensors, although you will see positive temperature coefficients occasionally. Negative temperature coefficients are the most common. We can see, however, that when it comes to our sensors, not only is there different types, thermistors, RTDs, thermocouples, and each one has their benefits and their cons, there's also what we'll see here, different types of sensing elements. The most common sensing elements are nickel or platinum, but there is copper. I don't run into it in specs very often. So what you'll see is that the platinum one has a more predictive curve across a wider temperature span, whereas you see nickel kind of has a less predictable curve. It starts to tilt right when you get into this high temperature range. But let's be real, outside of steam, we're not dealing with a lot of things that require us to be less than 0 Celsius, unless you're doing like ice storage or cold rooms, or something greater than 200 Celsius, unless you're doing steam, or you're yeah, basically steam is the primary one I run into with it. Let's keep going. So resistive inputs, these are going to be a input that is used for temperature sensing. Typically, I'm not going to get into constant resistance, but that is something you can use for different purposes, but that would just be confusing. Voltage inputs. So this is an example of a electro-pneumatic transducer. I use these all the time in a past life. And what it would do is, based on a PSI that it was reading, it would then go and send out an electrical signal. So this was a way to go and control, or sorry, based on the electrical signal it was reading, it would send out a pneumatic control signal, typically between 0 to 15 psi. So the purpose of this was to take a pneumatic actuator and be able to control it with a direct digital control system. So as part of a pneumatic retrofit, those pneumatic actuators can be thousands of dollars, and replacing them may not be feasible, and you may want to keep it for whatever reason. Maybe you're using it with steam, maybe you're in a corrosive environment where you don't want an electromechanical actuator. And I realize you don't know what actuators are yet. If you're a brand new technician, don't worry, we'll get to that in the HVAC components. But what you would do is you would take a 0 to 10 volt signal. Usually it would come in right here, and that 0 to 10 volt signal would be then converted, transduced to a pneumatic signal. There's this little pump in here that would, or there's a little valve in here that would regulate the control pneumatic signal, or pneumatic air, because there's main and then there's control. Main is your high pressure, and control is typically your 0 to 15, 0 to 20 psi. This would be regulated by this transducer to thus control the, in this case, pneumatic actuator or other systems, depending on what you're doing. Voltage inputs, right? So this is taking a voltage input. So what I want to be clear on, because this is something people get kind of crossed on a little bit, is that inputs are not just to your controller. They can also be to an end device. So as we'll see in next week's episode on voltage outputs, a 0 to 10 volt output from your controller could actually go to a 0 to 10 volt input on a field device. So everything you learn about inputs and outputs can also be applicable to your actual control devices in the field. So I want you to kind of start to visualize. Don't just be stuck on the controller, actually think of your control devices. Then we get to some current inputs. This is a humidity sensor, right? And we can see that this humidity sensor, this actually takes a power supply in series. So there's parallel and there's series. Typically, when you're doing 4 to 20 milliamp, it's in series. Typically, when you're doing 0 to 10 volts, it is in parallel, how you're wiring it up, or could be in series as well. It really just depends. Once again, multiple different manufacturers do this multiple different ways. Some of them source the control power from their controller. Some of them, there's just a variety of things. So if I'm not teaching exactly what your product does, do be aware that there are a lot of different products in the market. Suffice to say, we can see the power supply going in, powering this sensor, right? Because this is current, not voltage. And if we remember from Ohm's law, which you have not learned yet, but you will in the electrical video that we will have upcoming probably a month from now, that there is a relationship between current, resistance, and voltage called Ohm's law. So as we pass through voltage, we can vary the resistance and allow the sensor to read the resistance on the line. And that will then give us this 4 to 20 milliamp. There's a reason we do resistance. It provides less interference. It also provides us the ability to have a longer run. So if you have to run a sensor across a central plant and there's a lot of electrical interference, you may choose 4 to 20. Plus 4 to 20 gives you some failover capabilities, which we'll talk about in a future episode. Then you have digital inputs, which are sometimes called contact inputs. They're sometimes called dry contacts. I prefer the term digital inputs, and the reason why is because my input, what I'm truly sensing here, is two states. It's either open or closed, it's either on or off. I'm sensing a digital signal. I'm not sensing a resistive signal, I'm sensing a digital signal. The purpose of these would be things like current sensing relays. A current sensing relay would enable us to go, and I realize this is a current transducer with a 4 to 20 output, but ignore that. It was the best image I could find. So current sensing relay would sense current and then would close contacts based on that current to give status. And then you can actually set the current on that current sensing relay to a low enough current, or to a high enough, no, low enough, to a low enough that it wouldn't be, no, high. Geez, man, I am off. I think it's the 45-minute run I did this morning. My brain is still a little wonky. It's the longest run I've done in a while, so forgive me for that. You would set it higher so that it would actually show a load on the motor, because if you had it trip at a low amount, you could have a free spinning fan, like the wheel or the belt's broken and it's spinning and it draws just enough to trip the relay, but not enough to show that it's actually running. So under load. But suffice to say, these digital inputs, not only current sensing relays, these could be things like flow switches, pressure switches, etc. So, the AFS series 460, I believe, maybe 465 from Cleveland Controls, is the resettable pressure switch. That is a dry con or a digital input. It's a two-state input that comes into your controller and gives you a status. Then we have pulse points. I don't see these as much anymore. Maybe you all do. I saw them both in the electrical world. I also saw them in the irrigation world. So a lot of irrigation and flow sensors would send pulses to tell you kind of what flow you were getting. You would also have uh, electrical signals that would send you pulses. And based on the amplitude and how often and how long the pulse was, it would represent either some sort of kilowatt demand, kilowatt hours, and gallons per minute. And all of this is actually in the cut sheet for the sensor. It'll tell you. And then when you go into your controller and set it up, you would actually set, okay, what does a pulse mean? How long does it mean that? And this gives you an ability to calculate either electrical or hydronic flow. Then we get into logical inputs. But before I do that, I actually want to switch screens real quick and show you something. Here we go. You should be seeing a specification now. And in this specification, I've focused us in here on this outside air. So this is Oregon State University's, they call it a guide spec, but it seems to be for a specific project. What you see right here is humidity and temperature sensor, 2% accuracy, thin film capacitive replacement sensor element with replaceable sensor element with waterproof housing, 10K ohm type 2, and a two-wire loop power 4 to 20 milliamp signal. So it looks like we are getting two signals. 10K ohm type 2 is a thermistor. It doesn't specify whether it's PTC or NTC. And it also says two-wire loop powered 4 to 20 milliamp. So I'm assuming that that is meaning two things. One, 4 to 20 milliamp back to the controller for the humidity signal, and loop powered is just showing kind of the electrical details I showed you a little bit earlier. So you're sitting there, you're reading the spec, you just got sent out to a job, you've got to go to Granger or somewhere to pick up a sensor. How do you make sense of this? Well, the first thing, this is where we go back to those input types I just showed you. You have a resistive input. So the first thing I'm going to do here is I'm going to figure out what inputs do I need. Well, based on this, I need a resistive input, which is 10K type 2. And I also need a 4 to 20. Just through my own experience, I know that humidity being a linear scale of typically 0 to 10 is typically, or sorry, 0 to 100 is typically 0 to 10 volts DC or 2 to 10 volts DC or 4 to 20 milliamps. Those are the typical input signals to the controller. And then I scale match those to my humidity using like a reset or a scaler or whatever it's called in your control system. And then I also see my 10K type 2, which I know is going to be a two-wire resistive, and that's going to go to a resistive input on my controller. So from there, I would go to, and for this, I'm going to be using Kelly right here. And I always feel like I'm pronouncing their name wrong. But I'm going to go to their site. We don't endorse any company. I just they have a pretty easy site for me to navigate. I've ordered a lot of stuff through them, and but you know, your distributor or controls provider or parts warehouse of choice will most likely have the same equipment. But what I do here is I typed in outdoor air humidity. And now I start looking at this, trying to figure out what do I need. I know I need 2% accuracy. That's important. I know I need a 10K type 2 thermistor. And I also know I need a 4 to 20 milliamp signal. So can I find any of these that have that? I'm going to just click on this one right here because it says 2%. And I'm going to see what it has as far as capability. So it has a 10K type 2 thermistor. Okay, great. That covers me for that. And it has a 4 to 20 milliamp output signal. I typically like to go and look at the actual manual itself. which I will bring up right here. Give me 1 second. So 2%, okay. 10K type 2, so that's E. So I'm getting my part number here. I want 4 to 20 milliamp. This is universal, so 2-wire or 3-wire, and it'll also do 0 to 10. If I didn't want the display, if I wanted to save money, I could do the X and not get the display. I verify that it's 0 to 10. I verify that it's got temperature. I verify what I need for a power supply. If I'm going to do 4 to 20, I need a DC power supply. That's what I need. I go in here, verify my accuracy. Okay. And everything looks good for what I need. And so now I've gone and I've figured out, all right, this is what I need based on that specification. So I hope at this point you've seen me go and take what I know about my inputs, take what was in the specification, which I'm going to bring up again real quick. Here we go. Identify what I need. And you'll notice the sensor that I chose is not listed on here, but it says or equal. So that typically, not always, but typically if it says or equal, that means that I can just substitute it in. I don't have to submit and add alternate. I can typically just put that in. Some engineers of record or equal will mean they still want you to submit and add alternate. So just your mileage will vary. Know your engineers, know what they expect. This would be a good time, real quickly, though, to talk about two things. One, we'll be speaking at Niagara Summit. So if you're going to be at Niagara Summit, definitely stop in for our session on recruiting, training, and retaining. So we're going to have our director of business development talk about our approach there as part of a panel. That will be on Wednesday, April 17th at 11 a.m. And then we're also going to be doing an a panel on cyber fluency for the OT environment. So we're going to be talking about cybersecurity, specification, all of that will be on that panel as well. So I hope to see you there. And I'll share that one with you real quick, cyber fluency. So I hope to see you all there. Let's get back to the PowerPoint. Here we go. And back to the PowerPoint. So logical inputs. There are two primary forms of logical inputs, and they go by many different names. Some folks, as you'll see here, call them numerics and booleans and strings and enums. Some folks call them multi-state. Some folks just call them straight up AIs, BIs, AOs, BOs, AVs, BVs, etc. For the sake of this presentation and my sanity, we will focus quite simply on writable and non-writable inputs. So writable inputs are inputs of which someone can write to the input. And this is where it gets a little muddy. I'll admit that, because you can have non-writable inputs that are still writable. They're just not writable by the operator. So for example, I can go and add a numeric point, but have it, I can add a point that's an AI, for example, by mapping it in. It is a logical point. It's writable from the chiller that I'm integrating it from, because I'm mapping in the point, but it's not writable from the operator. So I can't override it. And I know some of you are going to be like, well, Phil, there's a variety of ways you can override AIs, analog inputs or binary inputs by bringing them out of service. You are correct, but I would argue that that's for testing, because technically when it's out of service, it should be out of service and no longer readable by the controls program. But that's, nuanced. Then there are writables. And the reason these are writable is because they have a priority array. A priority array is a more advanced concept that we'll get into when we start to talk about BACnet. Although the priority array is not necessarily a BACnet construct, all it is a multi-point array of which The highest number, input 16, is of the least importance, and input 1 is of the most importance. Some folks do a 0 to 15 priority array. I primarily, though, see a priority array of 1 to 16. So 16 is typically, so how it goes typically is 16 is global, 15 is local, 14 is local operator, and then 8 is operator override, and 1 is like emergency override. So there's some kind of standards behind what should be what, but the most common standards are just 16 and 8. Now here's the difference, or here's the important part of this. If you are going, and I've discussed this ad nauseum for those of you who have listened to our podcast in the past, if you're doing an integration, a backnet integration, and you map in an analog input or a binary input or a multi-state input, and it's zone temperature or it's chilled water temperature. You map that point in. I've seen a lot of people map those in and think that they should be able to command them. Those are not writable. They're not logical. They're not variables that are controllable. And so if you map in those inputs, you're not going to be able to edit them. Inputs are typically, logical inputs are non-writable and they're for data reading purposes only. Writable inputs, also known as variables, so you hear analog variable or analog value or numeric writable in Niagara, they basically all mean the same thing. They're just different systems, different naming structures. Those have a priority array and thus they're writable. And a little bonus point, the objects that are known as outputs. So in Niagara world, it would still be called a numeric writable. In other systems, it may be called an analog output, or it may be called a voltage output. And those are actually writable because those typically have a writable array as well. All right. So there you have it in a nutshell. Those are inputs. I started off this episode with saying that you'd be able to describe the common types of inputs. So you should be able to describe that there are physical and logical inputs, that there are resistive, voltage, current, contact, and pulse inputs, and you should understand why and how and when you use those, even if you don't understand exactly how to implement them. You should also understand that there are logical inputs and that those logical inputs are either writable or non-writable, and that the writable inputs, they're writable because they have a priority array. So there you have it, folks. If you haven't, definitely go and check out the rest of our podcast episodes at YouTube. If you want to be like Thomas and become a member, we greatly appreciate that. It supports the podcast that we deliver to you every week. I will also say everything will be available eventually at podcast.smartbuildingsacademy.com/460. My goal is to get all 3 of those episodes up this week because I know we're still waiting on 458 and 459 to get uploaded to the website. That's on me. And definitely, if you found value in this, please consider sharing it on your Facebook or LinkedIn by hitting the share button, tagging at Smart Buildings Academy, or going to Apple Podcasts or Spotify, leaving us a 5-star review, or going to YouTube and subscribing. I definitely appreciate all of you so very much. Next Wednesday, we're going to be diving into physical outputs. And then after that, it's going to be a recorded one because I'm going to be at Niagara Summit, but we're going to be talking through controller types. We're going to talk through application specific versus free programmable controllers. And we're going to get a little into BTL, classifications of controllers. And we're going to talk through that. And then we're going to go through the week after communication buses. The week after that, we're going to go through routers/supervisors. And then we're going to go through servers. And that should take us through the 4 tiers of the BAS architecture. And then we're going to move into HVAC, I think maybe electrical. So it's either going to move into HVAC or then electrical, or electrical then HVAC. It just depends on the questions I get. I'm going to pause here. Any questions you all have, I'm an open book. I really appreciate you all being here. And I will answer any questions you all have. Just feel free to ask. And I would be more than happy to answer whatever questions you all got. And with that being said, let me stop sharing that. And let me see what questions we have in the chat. I hope you all are finding these valuable. I know it's a little basic, and I know I'm starting off at a pretty simplistic point. My goal is that by the end of this series, which I envision taking about 3 to 4 months to get through, so about 12 to 16-ish episodes, there should be a solid foundation that I'll then put into a playlist that you all can go and share amongst yourself, and hopefully it just really helps upskill the folks who are trying to learn this. I also plan on doing some YouTube shorts that I'm going to talk through the industry, just why I believe young people should join this industry, the benefits of that. Let me see if there's any questions on LinkedIn. No. I know LinkedIn is kind of funky sometimes, and sometimes the questions sneak outside of that. No. Okay, they're not there. YouTube, not seeing any questions there, so we're good. All right. Well, hey, folks, everyone, I appreciate you. I will see you on Monday. I honestly don't know what episode we're going to cover on Monday. I'm kind of torn between where we're going to go with that. But for sure, Wednesday, we're going to be talking about outputs. If y'all need anything, hit us up on LinkedIn, hit us up on our website. And I hope to see y'all at Niagara Summit. Thanks so much. Take care.